Welcome to Operating Systems lecture 21. Alright, so last time we were looking at concurrency problems, right, and we said we looked at this code which inserts an element data into a list, right, and let's say this is a linked list. So the way this works is you declare a local variable, you allocate some node of type list from the heap, you set its data, you set its next pointer to the list, the list that's given as the first argument, and you update the list, right. So you are basically appending the data in the front of the list. Okay. Now, and we said that look, these two statements, let's call this statement A and let's call this statement B. These two statements need to execute in an atomic fashion. So while they are executing, they should not get interrupted, or nobody else should be touching this list while in the middle. So it shouldn't happen that in the middle of this another thread starts executing insert. If it does that, then bad things can happen, right, and the bad thing in this case would be that the list structure is no longer preserved. So for example, we saw last time that if it so happens that there are two threads T1 and T2, one thread executes A1, the other thread executes A2, and let's say it executes B2 after that, and then this one executes B1, right, then what can happen? You had a list, and thread 1 will insert its data, let's say this is D1, data 1, and thread 2 will insert its data to the same list, right, and you will have something like this. So the list will be pointing here and this is no longer a list now, right. So bad things like these can happen. Similarly, any other schedule which has A1, A2, A1 and D1 getting interrupted and another insert getting called on that list, bad things can happen. So another bad schedule is, let's say, A1, A2, B1, B2, right, or anything of this sort. So these are all bad schedules and these basically corrupt your data structure, right, or violate your invariance, right. So what did you want? You really wanted that A1 and B1 should execute in a sort of non-preemptible way, right. So, or in an atomic way, okay. So if it's possible that while A1 and B1 are executing, either no other call to insert should start, or no other call to A and B should start. So A2 should either be here, or A2 and B2 should have been before A1 and B1, right. That's what you want, okay. Right. So in other words, you want to say that these two statements A and B should execute atomically, and they should execute atomically with respect to something, with respect to themselves, right. So there can be other code that's running simultaneously, but as long as that code is not touching this list, it's okay, right. But if that code is likely to touch this list, then it shouldn't be, that code and this code should be atomic with respect to each other. Right, and so we said that there's an abstraction called a lock, right, that we're going to discuss today. So what are some? So when we are designing such an abstraction, what do we need to take care of? Firstly, in this function, these are the only two statements that need to be atomic, right. It doesn't matter what happens here, right. So it's only A and B that you need to protect. So you need some way of specifying that this is the area that's atomic. You don't need to make the entire function atomic, number one, right. Number two, it will be nice if you could say that operations on this list need to be atomic with respect to each other, but operations on list 1 and operations on list 2 do not need to be atomic with respect to each other. So insert on list 1 can happen concurrently with operations on insert on list 2, it doesn't matter, right. So you would like to have that kind of flexibility that allows better concurrency and better performance in general, right. And thirdly, it may not be just this function insert, right. So insert should be atomic with respect to each other, or these two statements should be atomic with respect to themselves, but these two statements may need to be atomic with respect to some other statements, right, because let us say there is another function called delete, right. So if delete and insert are happening concurrently, then similar situations can happen where the list becomes corrupted, right. So it is not just these statements being atomic with respect to themselves, these statements may need to be atomic with respect to some other code in your system, right. So that's the so one has to design an abstraction that allows you all these different flexibilities, right. So many different abstractions exist to solve this problem, right, and as you go along in this course or in future courses, you are going to come across different kinds of abstractions. Different programming languages have different abstractions, C will have a different kind of so Java or something like that would have different kind of support, and different languages will have different kind of support, but locking or locks are one of the most common types of abstractions used to solve this problem, right. So what is a lock? All right. So a lock is defined by a type, let us say the type is struct lock, right, or any other type. There should be a type which says it is a lock, right, and there should be two functions defined on this lock. One is called acquire, right, which basically represents that the lock has been acquired, right. So I am going to discuss what that means, and release. Right. So this variable, this structure lock is a stateful structure, and it represents two states, either it is locked or it is unlocked, or the other way to say it is either it is acquired or it is released, right. So that is the so lock has one bit state which says whether it is locked or not. The function acquire changes the state of that lock from unlocked to locked, but the precondition being that the state should have been unlocked earlier, right. So if it is already locked, then acquire will just wait till it becomes unlocked, and as soon as it becomes unlocked it will turn it to locked, alright. So that is the semantics of acquire. Once again, acquire will set this state of this lock to acquired state or locked state, but it requires that earlier it should have been in the unlocked state or released state, right. If it is already locked, then it will keep waiting till it becomes unlocked, and after it has become unlocked it will set it to locked, right, and release will just set it to unlocked, right. So that is basically it, right. And let us assume that these functions are are implemented in some way. How they are implemented, we are going to discuss this later. But so what happens is, if two threads try to acquire the same lock simultaneously, and let us say initially the lock was unlocked, so let us say initially the lock is unlocked and two threads try to acquire this lock simultaneously, only one of them will be able to lock it and the second one will keep waiting, right. So that is abstraction. The second one will keep waiting till what time? Till the first one calls release, right. So in other words, there is an invariant. The invariant is only a lock can only be acquired by at most one thread at any time. It's only one thread could have acquired the lock at any time. The second thread will have to wait. Only out of the first, let us say there are 5 threads or n threads, then other n minus 1 threads will have to wait, right. Only when the first thread calls release is then somebody else going to get a chance to get the lock, alright. Okay. So what is it doing? It's basically doing, if multiple threads call acquire, then it's serializing these threads. It's saying, oh, multiple threads have tried to call acquire, so if multiple threads, let's say, call acquire, and let's say they come at the same acquire point, from here on, let's say only one thread will get to run. Only when it calls release then the other thread will get to run. When it calls release, the third thread is going to run, right. So it has serialized the execution, but it has serialized the execution only for the region which was within that acquire and release calls, right. Okay. So let's see what will happen in this case. So we had this code, we had this function called insert that inserts data into a list, and we were not happy with the fact that this code could be executed concurrently by multiple threads. So what do you want? You want to serialize the execution of this code, right. So one way to do that is define a lock, all right. Define a lock, and initially let's say the state of the lock is unlocked, and just put lock calls to acquire the lock and release the lock, right. I think there is, let's call it lock. So acquire lock and release lock, all right. So this makes the code correct, right, because if there is one thread, it will come here, the first thread will be able to acquire it. While it is inside this, another thread who tries to execute the same code will not be able to acquire the lock, so it will have to wait. So you have disabled concurrency in this region, right. So this region which is protected by locks is also called the critical section, right. So critical section is a region of code that needs to be serialized in its execution, and the locks are basically allowing it to get serialized. Yes, question.
Concrete threads which you are talking, they are on different CPUs, or they can be on the same CPU?
Right, okay, good question. So what are these concurrent threads which I am talking about? Are these on the same CPU or are these on different CPUs? Same, okay, 6 or okay 10-15 people, different, right. Actually it does not matter, all right. It can be on same CPU, it can be on different CPU. Let us look at how threads work, right. So
if it is on the same CPU, and if suppose I have acquired a lock and then it gets
right. So let us look at what happens. Let us say there is one CPU, right, and let me just draw that diagram that we have. This is the bus, and let us say this is the memory, right. In the memory there lives a list, right, and what is happening was that this CPU was trying to update the list, right, and while it was in the middle of updating the list, it is possible that a timer interrupt comes, right, and the thread that was executing gets preempted, or it gets switched out, and another thread gets to run, in which case what will happen is, while I was executing at this line, an interrupt comes, I get context switched out, the other thread gets to run, and I have the same problem as earlier, right. So this problem exists even with one CPU. If you have multiple CPUs, the problem still exists, it maybe becomes a little bit, the probability becomes higher, because it is possible that one thread is executing here and another thread is executing on this CPU, they are both trying, now there is no interrupt involved, right. So there is no interrupt involved, but both these threads are trying to simultaneously access list, and the same thing, the same problem can happen. So the problem is really about interleaving. The interleaving can happen either because of switching out on the same CPU, or the interleaving can happen either because of physical concurrency of physical CPUs on physical memory, right. In either case the nature of the problem remains the same, all right. Okay, I have a question for you. Does the problem exist for user level threads, or does it only exist for kernel level threads? It exists for both, right. It does not matter whether it is user level thread or kernel level thread, it exists for both, because at the end of the day the abstraction is that a thread can be switched out any time and another thread can get to run. At every instruction boundary a thread is potentially switchable, alright. So it doesn't matter. Okay. All right. Question.
Sir, suppose like the example you gave, in case of multiple CPUs, sir, does this lock will say like stop all the other threads running in all other CPUs and just
Okay. So now, so let's say what happens with the lock, right? So we said there's a list living in memory. Now in our new abstraction, we also have this function, this extra variable called lock living in memory. All right. And now both these CPUs, if both these CPUs try to acquire the lock at the same time, somehow this acquire function has been implemented such that only one of them will succeed, the other one will have to wait, right? How it is implemented we're going to discuss in a minute, but let's just say that there is this magic function called acquire that allows us to do it. Okay. All right. So assuming that there is such a function, life becomes easier. I can put a lock around my critical section. All right. In fact, notice that this abstraction allows you to say that this is the critical section. I don't need to say the entire function is a critical section. So I can I can just protect this area, and these lines can execute concurrently. So I don't need to impede performance on the other lines. The other thing is, if let's say there's another function called delete, and delete is going to do some manipulations on the list also, then what do you need to do? Wherever you are doing those manipulations, you need to use the same lock there, right? You need to make sure that you're using the same lock in both insert and delete. So that way you can prevent, you can make sections of code atomic with respect to each other by using the same lock around those critical sections, right? Thirdly, the third thing I said was I may want to say that look, this list and this list do not need to be aware of each other. They can proceed concurrently. So in this case, am I preventing that? So if I insert in one list and if I insert in another list, will they get serialized? Yes, right? They will get serialized because I have one lock, and I'm calling insert on L1 and I'm calling insert on L2. The same lock is going to get taken, and so only one of them is going to go forward. Even though the lists were different, I didn't need to serialize, but it will get serialized. Is it wrong to over serialize? It's not wrong. The program remains correct, but performance gets affected, right? So what would have been a better way? Better way would have been, let's have a lock per list, right? Let's say I have, let's say I have an array of locks, right? Or better still, in the list structure itself, I have a lock, right? So instead of saying acquire lock, I say acquire list.lock or something, right? So in the list structure itself, I have a lock. So this is a lock for this list. So if you're manipulating this list, take this lock. If you are manipulating that list, take that lock. But these two locks are separate locks, so you can do these concurrently, right? So that's the nice thing about locks, they give you a lot of flexibility, right? Okay, now let's see how locks are implemented. So what do we need to implement? We need to implement a structure called lock, right? And let's say I implement it by having a field inside the structure which says whether I am locked or not. I said this is a stateful abstraction. It basically has one bit of state which says whether I am locked or not. So let's say this is the state, well, locked. Yeah.
Can we have lock on subset of data structure? Maybe like a tree. There is a tree, and I only want to lock the left structure of the tree. Is it possible?
Can we have a lock per subset of the data structure? For example, if I have a tree, then I want to only lock one subtree and not the other side of the tree. Is it possible? Yes, it is possible. Okay. How it's done? I mean, we're going to see as we go along the course. All right. Okay. So let's see. Void acquire struct lock star L. Right. So I need to implement this. What is one way to implement it? Well, it's one very simple way is just check, right? So just check is L dot logged is equal to 0. If it is 0, then very good. Just set L dot logged is equal to 1 and return, right? But if it's not 0, then keep waiting. So let's say to wait, I just put a while loop here, right? So basically I check if L dot locked is equal to 0. If it is 0, then actually let's say not equal to 0, right. So while L dot locked is not equal to 0, I keep spinning. As soon as I find it to be equal to 0, I set it to locked, right. But if it's not equal to 0, it means it's already taken, I cannot take it, I need to wait, right. And the way I'm waiting is I'm just checking it over and over again in a while loop, alright. And how do I implement release? Let's say L dot logged is equal to 0, right. Release is simple. I don't need to do any waiting, I just need to revert the state back to 0, right. So that's acquire and that's release. Is this correct?
So, but how do you define the preference between functions? Like, suppose there were delete and insert, and suppose locking was occurring.
Okay.
So it might have been the case that first.
All right. So question is, how do we define the preference, right? So preference. Let's say there are two threads. One of them is calling insert, the other thread is calling delete. Who should get first, right? Well, the order can be completely arbitrary, right? The lock abstraction doesn't say that, doesn't give an order. In general, you would just, from a performance standpoint, what is the best policy? Well, one good policy is first come first served. Whoever comes first, give him the lock. All right. Whoever comes second, has to wait, irrespective of what function you are executing.
But then things would not be predictable.
Then things would not be predictable from what will happen in sense of way. Yes. So there is still some non-determinism even after you have locks. It's possible that this happens, right? Thread 1 executes before thread 2, or it's possible that this happens, thread 2 executes before thread 1, and both of them will result in different final values of your memory, right. So this is called non-determinism. There is still some non-determinism in your system, depends on who gets there first, but the important thing is it's correct, it's not wrong. Earlier it was wrong because I was allowing this and this is wrong, it was corrupting my data structure. This was right, and I am allowing both of them, and there's still some non-determinism in your system, right. In general, it's a very interesting thing that systems need to be non-deterministic for performance, right. So it's a very fundamental thing. If you make a system very deterministic, you lose performance, right. So let's take an example. Let's say I wanted to make my system deterministic. So I say, this lock will always be taken in strict round robin order. First thread 1 will be, I know how many threads there are, let's say there are 2 threads. So first I'll give it to thread 1, then I'll give it to thread 2 and so on, right. Thread 1, thread 2, thread 1, thread 2. So if thread 2 reaches first, then I'll just have to make it wait, even though let's say thread 1 is lagging behind for whatever reason. Let's say thread 1 is executing on a slower CPU, let's say thread 1 didn't get enough time to execute while I was doing it. So for all these, or any other reason, thread 1 in general has more code to execute than thread 2, right. All these are possible cases. In either case, if thread 1 is lagging behind thread 2 and thread 2 reaches the lock first, if you want to have complete determinism, then you'll have to make thread 2 wait, which is just waste, right, because there's nobody who is actually executing in that region. You could have executed it correctly, you could have let thread 2 execute first, but you have to make it wait. So non-determinism allows performance, and lock abstraction in general does not thwart non-determinism. It allows you to provide correctness, but there's still some non-determinism in your system. Okay.
Is it possible two threads are working on the same list and one thread acquires the lock but the other thread releases the lock without acquiring it later?
Okay, is it possible that one thread acquires the lock while the other thread releases the lock? So is it possible for a thread to release a lock without acquiring it? It's possible, but we are assuming that because they are threads, they are mutually trusting each other, right? So it's the programmer's mistake that he has he has called release without acquiring the lock. It's his problem. He will pay for it by some error in his program, unless he's doing it very carefully. All right. So notice that because we are operating in the threads environment, we are basically saying that we are trusting other threads. So threads must acquire and release put acquire and release around all critical sections appropriately. They should not call acquire twice without releasing. One thread should not call acquire twice without releasing. release shouldn't be called without calling acquire and all that. So these are all invariants that the programmer needs to maintain. So the headache is programmers.
So, but if the struct log maintains a list of threads which have acquired it, then maybe like in the implementation themselves we can check these policies.
Right. So firstly, a lock cannot be acquired by multiple threads simultaneously, right? A lock can be acquired only by one thread at a time, right? So it's not a list of threads that has acquired the lock. It's only one thread that could have acquired the lock at any time, right? And the other thing is, when you're using a lock, it's better to not rely on the implementation of the lock, so that you can change the implementation underneath. Just look at the abstraction. The abstraction is there is a structure called lock, and there are these two functions, acquire and release. Don't make assumptions about how the acquire and how the release are implemented. In general, that's how it's done, so that the implementation of the abstraction can be changed later at will. Right? So this is the standard practice, that you will rely on the abstraction. Okay, let's come back to this implementation. Is this implementation correct? Yeah, go ahead.
So can I context switch while I am locked? Like when
Can I context switch while I am holding the lock? Yes. Right.
Then the other threads cannot do anything, because since I have locked it.
Alright.
So it's basically wasted of some performance.
Okay. So yeah, very interesting question. If I have a lock, I have taken a lock, I'm in the middle of the critical section, a context switch happens, another thread gets to run. If that thread also tries to take the same lock, then it will just have to wait, alright, till the next context switch, and there's some wastage of performance. Absolutely true. How these things are handled, let's talk about it in some time. Actually, this question about whether a context switch can happen while you have taken a lock or not really depends on your implementation of how you have implemented the lock, alright. So, but in any case it's correct, right? So let's talk about correctness first, and then we're going to talk about performance.
So if like thread 1 see that lock value is 0 and that context switch will take place, and the other thread will also see that the value of locked is 0, then
Okay, good. So you're talking about a problem in this implementation, yes? So so everybody understands there's a problem in this implementation? Right. Okay, the problem is one thread comes here, it sees that locked is equal to 0, it's here, a context switch happens, or forget about a context switch, let's say it's a multiprocessor system, another thread also comes here, and both of them are here, both of them take the lock, you have broken your abstraction, right? The abstraction is no longer true. So what did you want? You wanted that this entire thing should have been atomic, right? So what have I done? I have just, I had some critical section that I wanted to make atomic. I said I'm going to use locks to protect that critical section, but now I have changed the problem to say now I have to implement this lock, but now to implement the lock also I need some atomic invariant, right? So I haven't really made any progress, except I made some progress in the sense that I have reduced the critical section from that large area, which can be arbitrarily large, to this small thing here, right? And now the question comes, how does one implement this in an atomic fashion, right? Okay, all right, so the answer is you need hardware support. Okay, so there should be some instruction in the hardware that allows you to read and write a variable in an atomic fashion, right? So I'm going to take the example of x86. On the x86 there is this instruction called exchange, right? And exchange takes two operands, a register and a memory address. Okay, so for example I could say, and the semantics are that it's going to exchange. So this is the exchange instruction, and it will exchange the contents of register and memory. All right. So if let's say initially, so before r is equal to 0, m is equal to 1, then after you will basically see r is equal to 1 and m is equal to 0. Right. So that's the semantics of the exchange instruction. Notice that this instruction is doing two memory accesses in one instruction, right? It's reading the old value of m and it's writing the new value of m. So it's it's both reading and writing in one instruction, right? So that's important, So that in that sense this instruction is slightly special because it needs to read and write memory, so it needs to make two memory accesses in some sense. Alright, okay, and it's possible to make an instruction atomic in hardware. So on x86 there is this lock prefix, so if you say lock exchange RM, then this instruction will atomically read the value of M and overwrite it with the new value such that no other CPU can intervene in the middle, right. So what does it mean? That if let's say there is CPU 0 and CPU 1 that both execute exchange on address let's say 100, right, and let's say I am saying, so this is address and this is value let's say R, and let's say R was equal to 1, and this one is saying exchange to the same address, and let's say this was 0, then either this will happen before this or this will happen after this. It's not possible that the two reads and writes of one instruction get interleaved, right. So for example, right, so let's say initially the 100th location had value -1, then and let's say CPU 0 executes before, so -1 comes to R and 1 goes to M, right. So this was initial of, right, so let's look at this again in a bigger context. So right, so let's say initially M is equal to -1, if CPU 0 executes then M will become 1, and if CPU 1 executes after that M will become 0, right, and so the final value will be 0. On the other hand, if CPU 1 executes first then it will become 0, and CPU 2 executes later then becomes 1, right. What's not possible is that they get interleaved, right. So what can happen if they get interleaved? Both of them read the old value of M, and so in this case, you know, CPU, so R0 would be equal to -1 and R0 will be equal to 1 in case of CPU 1, right. In this case R1 will be equal to -1, or R0 of CPU 1 will be equal to -1, let's not call it R0, let's say R is equal to -1, R is equal to -1, R is equal to 0, right. So these are the only two possibilities. If two threads, two CPUs try to execute exchange, they are atomic with respect to each other. What cannot happen is that both of them read the old value of M. So it's not possible that CPU 0's R is equal to -1 and CPU 1's R is also equal to -1, not possible, right. This could have happened if both of them read the old value, right, and then they try to overwrite the new value, and so in that case exchange wouldn't have been atomic with respect to each other, right. Okay, this clear? Basically what I am saying is that the exchange operation itself is atomic with respect to itself and with respect to any other operation on that particular memory address, okay. Alright, so with that let's see how I am going to implement acquire. I am going to say void acquire and I am going to use some register. Let's say I use register EAX and I am going to put a value called 1 in the EAX. Then I am going to do exchange EAX with L dot locked, right. Whatever is the memory address of L dot locked, okay, and I am going to do it in atomic fashion, so I use a lock prefix here. So and then I am going to check if EAX is not equal to 0, do what? spin, right, else return, right. So I have taken the old value of logged into EX and put the new value of EX into logged. So in one instruction, in one go, I have read the old value and I have put the new value into logged. If the old value was 0, which means it was unlogged, then I am done. If the old value was 1, it means it was already logged. So I didn't change the value of logged either, so I just keep retrying this. This is clear? So this is my register. I've set it to 1. I'm trying to push this value 1 into logged, but I'm also making sure that the old value of logged should have been 0, right. So that's what I'm checking here. If the old value of logged was not 0, then it basically means that the lock was already logged, so I keep trying again. So what's the difference between the old code and the new code? In the new code, I'm using this exchange instruction to read and write the value of logged in one go, right. So if there are two threads which are trying to acquire this lock at the same time, one of them is going to hit the exchange instruction first. Whoever hits it first is going to get the lock and is going to return. The second one is going to see the value of log to be 1.
The one which cannot acquire the lock will keep on performing this exchange operation again and again.
Yes.
Won't it be wasteful then?
Okay, so yeah, good question. The thread which is not able to acquire the lock will just keep executing exchange operation again and again. Isn't it wasteful? The answer is it depends, and I'm going to discuss. But let's first talk about correctness, right? So good. So you just check if it was already locked. So and this is correct, right? Because you have made sure that you're reading and writing this log variable at once. Okay, good. So as was pointed out, one CPU will keep trying and the other CPU will fall through. So the one CPU that's trying is waiting, and it's waiting in a loop. Alright. So it's also called spinning. Alright. And this type of a lock implementation is called a spin lock. By the way, how will you implement release? The previous one is okay, right? It doesn't matter, just set it to 0 and that's fine. Okay, so release is fine, only acquired needs to change, release was okay, right? And this is called a spin lock. Okay, so in this example, what will happen? If two threads come on acquire, one of them is going to start spinning, the other thread is going to start running this code. Only when the first thread releases, the second thread which was spinning here is also going to get the lock, and the second thread is going to do it. So you basically serialized this operation of A and B, and you're basically doing it using the exchange instruction. Alright. So now there's a question, isn't spin wasteful? Okay. So what's the alternative? Okay, so there's one answer which says, can we disable interrupts? Would that be better? Just disable interrupts and then enable it at release. So disable interrupts at acquire, enable interrupts at release.
So not enabling at release, but once we acquire the lock, we can enable the interrupt. What's the problem?
Okay.
Is the critical state is there?
Okay. All right. So here's one suggestion. The suggestion is in this code here, right? Disable interrupts here. So call CLI here, CLI, clear interrupts, and then re-enable interrupts here, right? So on x86 the instruction is tie, set interrupts, right? So call CLI before and call STY after, and that should solve the problem.
So but that will only solve the problem within the same CPU if you have multiple threads.
Okay, so one answer is this will solve the problem only if there is a single processor. If there are multiple processors, it doesn't solve the problem. Perfectly fine, right? Okay, that's perfectly valid answer. Let's assume there was a single processor. Is this correct?
So if some other thread has an exception, then it will be the signal.
I have cleared the interrupts. I'm spinning, and let's say log was equal to 0, no, it was equal to 1. So I'm just waiting for it to get 0. If there's just one processor, will it ever become 0? No, because I have cleared the interrupts, right? timer interrupt cannot occur, and so what's the hope? I'm just basically deadlocked, right? So it's not correct. Secondly, a user program can definitely not do CLI and STI, right? These are privileged operations. So this privilege is only for the kernel, but even for the kernel this implementation is not correct. What could have been correct? Well, if you really want to do it in this way, one way to do it is inside this loop of while, give the other thread a chance, right? So just do sty and cly here, alright. So you are just disabling, enabling interrupt so that there is another thread who gets a chance, so at least there is no deadlock, right. This is actually a valid implementation of a lock on a uniprocessor, but it's not a very nice implementation, really, right.
So this is also equally wasteful.
This is also equally wasteful, right. Okay, and it doesn't work on a multiprocessor, okay, all right. But in either case, in both cases we are doing spinning, right. What's another way? Yield, yes, good. So the other way is yield. So if one thread has figured out that it's not getting the lock, has checked the value of the logged variable, it is 0, it's 1, it knows that it has to wait. Why are you still holding on to the CPU, right? So one way to do it is we could say that, okay, in that loop just call yield, right, and so yield is going to suspend you, and so that way you may let other processes run. But is it really a better way? Let's look at this example, right. In this case the critical section is really small, it's just two C statements which may be maximum of 10 instructions, right, or let's say maximum of 100 to 500 nanoseconds to execute these two statements, right. The other thread, how long will it have to spin? It will probably have to spin for around that time, which is 100 to 500 nanoseconds. How long will it take to actually call yield? Let's say 1000 or 1000 instructions, which is much larger. It's much better to just wait for 10 instructions rather than call yield, which is going to actually change my process structures and all that, and it's going to cause much better. So in this case it's actually better to use a spin lock. In fact, yielding is wasteful, right, because yield, there is a cost to yield. Imagine if there were two threads that tried to acquire the lock, one thread got it, the other thread called yield. Now this thread will very soon release it, right, and the second thread should have actually now got the lock, but now it is in this separate code path where it's calling yield, and then later it will get scheduled after the next timer interrupt or whatever, and so it's wasteful. Spinning would have been better. On the other hand, if the size of the critical section was large, let's say you were executing 10,000 instructions, or if you were making some external access like a disk access, right, or some other slower device, if your critical section is large in time, then it would be better to call yield, because for that amount of time you are just unnecessarily holding up the CPU, right. So isn't spin wasteful? The answer is depends. And depends on what? On critical section size, right. And basically the logic you want to use is, if the critical section is likely to be large, then use yield, right, and the lock which uses yield is basically called a blocking lock. In fact, instead of using yield you could actually also use block, right. So what is block? Block basically just says that I want to block myself because I know that this lock is not available. So yield just puts you in the runnable state, which means on the next scheduling quantum you will again get to run. Block basically tells the operating system that I am not even in the runnable state, right, I am in the blocked state, which means don't even schedule me, and at the release time the thread can say look at all the blocked threads and make them runnable, right. So that's another way. One is yield, the other is block. Block is even more conservative in the sense that if one thread is not able to get the lock, it blocks. The thread which has the lock, when it calls release, is going to unblock all the blocked threads, right, and again there is some cost to block and there is some cost to unblock. right, and that kind of a lock is called a blocking lock. Right. So we saw a spin lock. There is another lock called as blocking lock. Blocking lock will block the thread which called acquire, and the release function becomes a little more complicated because it unblocks the threads that are blocked on that lock. Right. So which one should you use? So typically you will have both implementations available, a spin lock and a blocking lock, and depending on, so as a programmer you have to make a choice, and you will basically look at your critical section size, typical critical section sizes, and make a choice. It's possible that your code is such that some critical sections are very small, some critical sections are really large, and the same lock is protecting those critical sections. Possible, right? Some critical section is small, another critical section is large, the same lock is needs to protect both those critical sections. What do you do in that case? Well, you can just say I will use a hybrid approach. I will spin for some time, and then if I don't get a lock in that time, then I'll block. Right? Even that's a valid strategy, and that's a strategy that's used in many lock implementations, which says spin for some time, right, and then block. If while you were spinning you got successful, you're done. But if you spun for some time and you have not got the lock, it probably indicates that, assuming that, so it's probably indicates that it's going to take a long time, so it's better to now block. Right? So this is sort of a hybrid approach, adaptive approach, where basically you at the runtime figure out whether you need to spin or block. So how do you decide this sometime? Whether it should be 10 nanoseconds, 10 milliseconds, 10 microseconds, 10 seconds. Once again, it's a decision that you have to make depending on what is the cost of blocking. Right? How long does it take to block? Let's say blocking cost is, let's say there's this variable, there's this quantity called the blocking cost, which says how long will it take to actually block this thread. So let's say the blocking cost is let's say 100 microseconds. Right? So if you know that the blocking cost is 100 microseconds, roughly speaking, then one approach is that spin for 100 microseconds, and if you don't get the lock in those 100 microseconds, then block. So now you're going to, so the maximum amount of time you are going to waste is 100 microseconds of spinning plus 100 microseconds of blocking, a total of 200 microseconds. Right?
So you said yield is costly, right?
Yield or block is costly, yes.
Sir, but suppose even if I'm spinning, we can't proceed until somebody has actually released it. But for that thread to run, actually it will have some time to, it will take the time to switch out, and
Yes.
that overhead is already coming in.
So can you repeat? I didn't understand the question.
Sir, I'm saying that you said we don't, for small ones, we don't need to call yield.
Yes.
And I'm saying that suppose another thread was running, suppose one thread was got spinning state, so we need another thread to actually release the lock, right?
No, so I'm talking about a multiprocessor system. On a multiprocessor system, you have to make this choice between spinning and blocking. On a uniprocessor system, what is the better choice? So how many say spinning? Okay, 3. Blocking? Right, most of the others, yes. So blocking is the better choice, right, on a uniprocessor. Because if you're in a uniprocessor, you're trying to get a lock. Spinning is not going to solve the problem, right? You're in a uniprocessor. If you keep spinning on a uniprocessor, you're never going to see that lock released because nobody else is getting the chance to run. It's only when you get switched out will somebody get a chance to run and he'll release the lock. So it's, anyways the switching is going to happen. So might as well just block. Right? So when I'm saying there's a trade-off between spinning and blocking, I'm really talking about a multiprocessor system. On a uniprocessor, it's very clear, always block.
So at the user level, even if it's spinning, it gets preempted, right?
Yeah, so even on a uniprocessor, it's also okay to spin because you will get preempted. So it's okay to spin, but from a performance standpoint, it's better to block. Right? From a correctness standpoint, it's also okay to spin, or even on a uniprocessor. All right. Okay, good. All right, let's stop here.